Here's a radio that I've had for quite some time. A Sears Solid State 8 AM pocket radio and accessories. Still in the original box, obviously. We have the original Silvertone owner's manual, which Silvertone was Sears' house brand. And the model numbers for this radio are 7208, 209, 210, and 211 to designate different colors. And by the model number, I'm going to guess this is a 67 model. We have our earphone. And we have our radio itself. Now the radio itself doesn't say Silvertone on it, it says Sears, which by the late 60s, Sears was phasing out the Silvertone name, so that just further confirms my suspicions that this radio was made in the late 60s. This is a rather well-built set with a metal chrome-plated front, heavy plastic back cover. I think this might have been their top-of-the-line pocket radio for that time period. Now there's a story behind this set. Whenever I was about probably 12 or 13 years old, just getting started into old radio collecting and electronics, I ran an ad in the local paper looking for old radios. Well, one day while I was at school, this gentleman called the house, and he likely didn't know that he was going to be talking to a 12-year-old kid, but anyway, he called the house and talked to my parents, and they told him all about me, and he told them, well, I'd love to talk to your son. I've got some radios and stuff, and I was in the radio and TV repair business for a number of years, and maybe I can help him out. So when I got home from school, my parents gave me the message, and they told me to give him a call, and they reminded me that he was in the next county, so, don't stay on the phone too long now. So I called this gentleman up, and we got off to a good start, and we kept in touch up until he passed away in early 2000. He was one of the many gentlemen that took time to help me out as a kid, as far as teaching me things about electronics and old radios and such. And I'll always have a special place in my heart for this gentleman, along with all of the other people that helped me out over the years when they could have just as easily sat back and not given me the time of day, but they took time to help me along and encourage me, and I'm forever grateful to those people. And to this day, I still remember those acts of kindness, and I always try to help other people out when I can, whether it be with electronics or just helping them out with life in general. I always try to give back when I can. However, the story is not over. A few weeks ago at church, my pastor's grandson, who I've become friends with, was getting ready to leave for the Marine Corps. And the Sunday before he was supposed to leave, we all went out to eat lunch after church, me and my pastor, the pastor's son, the pastor's grandson, his girlfriend, and then his girlfriend brought along a friend of hers. Well, to make a long story short, the friend of hers turned out to be the granddaughter of the gentleman that gave me this radio all those years ago. It's amazing what a small world we live in. So I'm going to check this radio out and see what kind of operating condition it's in and offer it back to the granddaughter and her family if she'd like to have it back. If so, if she would like to have it, I'll be more than happy to give this back to the family. But right now, let's open it up and see what the inside looks like. And here's the model tag from inside the radio. This came in black, brown, white, and blue. Obviously we have the brown version, so that would make it a model 7209. And here is the inside of the radio. This took one of those cylinder looking 9-volt batteries. It looks similar to a AA battery. I'm really not sure those batteries are available anymore, but if need be, we can probably add a modern 9-volt connector to allow the set to use a 9-volt battery. And the chassis number prefix is 132, so that tells me that this radio was built by Arvin for Silvertone, or for Sears, likely made in the United States. And unfortunately, I can tell in years past that a battery has leaked inside of this set. So let's clean the battery contacts and apply power and see if this thing still plays. And we're connected and turned on, and unfortunately we're dead as a doornail. And not surprising, ain't no telling what the battery acid done to this. But let's see if we can make it sing. But they were nice enough to give you a nice big schematic. Here is part of the instruction manual. Something you're not going to find with today's electronics. In today's world, you're doing good to even find anybody that can fix this new junk. Okay, we have the chassis removed from the cabinet. And unfortunately, there's some very extensive battery corrosion here. And one of the leads from the speaker was corroded off from the earphone jack. So I don't know if this is going to be a success story or not. We are going to give it all we've got, though. If we can't get this thing playing, it won't be because we didn't try. The first thing I want to do is clean off as much of this battery corrosion as possible, and then we'll go from there. Okay, I've cleaned off as much of the old battery corrosion as possible, and I jumped out the broken speaker connection, and as you can hear, we have desirable results here. So now all we need to do is fix the speaker connections and put it all back together, and this thing ought to be good to go. Okay, here we are back together. I've repaired the defective wiring and installed a modern 9-volt battery connector. And when I did that, the back cover wouldn't fit, and the only way I could make that happen was to break off these two little supporting tabs that were there to hold the original type 9-volt battery that's in place. And of course that type of battery is not widely available anymore. But now everything fits back together like it should. And here we are back together.
As a goal is one of
Don't have a lot of time left, so I'm not going to spend much time on any station. But it appears to be pretty sensitive for a little pocket transistor radio. Okay, there you go. Thanks for watching, and more to come later. I think that's WSM. Here's a GE Model 671 AC-DC battery-operated tube portable radio from probably around 56 or 57. This is probably one of the last tube-type portable radios that GE made. In fact, somewhere around 59 or 60, GE made a radio that was in a case that looked just like this. It was a transistor set that would run on either batteries or AC current. In 59 or 60 was kind of early for such a radio. And with this set, I even got the carrying case that goes with it. This was a eBay purchase. It was a little bit mislisted. They had it listed as a transistor radio and claimed they couldn't test it because they didn't have the right battery. Well, I guess they didn't know about the AC power cord hidden in the back. Okay, we're plugged into the metered AC power supply. We'll now turn it on and see if we have any activity. Well, have a little bit of current draw there, which means something's going on. However, we're getting no noise whatsoever from the radio. That means it's broken. Imagine that. Okay, let's open it up and see if we can change that situation. Okay, here's the inside of our radio. Here's the main chassis, which is on a printed circuit board, contains 4 tubes. This is our power supply unit, which we'll concentrate our efforts on first, and obviously that's the speaker. This radio, if you choose to run it off of batteries, it takes 2 batteries, a 7.5 volt battery pack for the filament, and then a 90 volt battery pack for the B+ voltage. Now those battery packs haven't been available as a reasonably priced mainstream item in probably 40 years or more. I know a few years ago I looked up, I think it was a 67.5 volt battery for one of these types of radios, and I think Eveready still carried it as a special order item, but it was some ludicrous price, something like 50 or 60 bucks for a battery, which is totally nuts. So if I ever want to run this on batteries, I'll just have to build a pack using modern cells. And this set uses a double-sided printed circuit board, so it just goes to show that double-sided PC boards are nothing new. They were around back in the 50s. Motorola and GE loved them. Most service technicians hated them. In fact, some of the traces on this board are starting to lift, so we'll have to be very careful when working on it. Okay, let's get this power supply unit out and see what's up with it. Okay, now that we have the power supply out, the next step is to remove this printed circuit board, and we'll just replace every capacitor on it, and that should magically cure our problems. No, actually what I'm going to do is troubleshoot this thing and try to figure out exactly what's killing it. Okay, this is our power supply board. This is our selenium rectifier, which may have to be replaced. They were even nice enough to put a fuse in here, a 200 milliampere slow blow fuse. Might go ahead and replace this capacitor. I believe this is an across the line AC capacitor. Its purpose is to keep noise and junk off of the AC power line from getting into the radio, and these capacitors are bad about exploding, so we might just go ahead and replace this with a AC safety capacitor. Okay, we've replaced our capacitor and we slipped tubing over the leads to prevent any possible shorts. Now I want to fire this up and check our output voltage here on the selenium rectifier, which will be at this point here. A common problem for these is for them to become weak, and they may output voltage, but it may not be nearly enough, and that's what I'd like to determine right now. Okay, let's check our voltage and see what we have. We have about 129 and climbing, which probably means the selenium rectifier is okay. We'll have to look elsewhere to see what's going on with this radio. It may be just something as simple as an open tube filament. Okay, I now have the chassis pulled out and exposed for servicing. I also have our schematic diagram here. Here's our power supply. AC comes into the selenium rectifier. And then we have a resistor here, and the B+ is taken off of this resistor. And that voltage should be 123 volts, which is in line with what we were reading. Then we have this 2200 ohm resistor that our filament voltage is taken from. This is a series filament circuit. All the tubes added together equal 7.5 volts. And I'm sure the reason they did that is because in a series circuit, all branches of the circuit must have the same current, so in other words, equal current for a series circuit, which means less battery drain. If they wired the tube filaments in parallel, we'd have more current draw because our branches, the current that each branch consumes would add up. So that's probably why they went with a series string here. But yeah, our filament voltage comes off right here, and that's what I'm interested in now. Okay, I think I've located the problem. I think this big filament dropping resistor is open. On one side of the resistor, we have 133 volts. On the other side of the resistor, we have Zippo. Here's our resistor, a 2.2 k ohm. As you can see on the meter, it's wide open. Now, this is what we call a flex resistor, and the reason they went with these is cases like this radio where they needed to fit a high-powered resistor into a tight space, so to speak. In today's world, I don't know if I can even get one of these resistors. I might have to go with a conventional power resistor and then come up with a creative way to mount it. I don't know how many watts this resistor is because the print on the schematic is really not that legible, but I can use Ohm's law to figure out a suitable wattage resistor to replace this with. Okay, I've drawn up a basic schematic diagram of our filament circuit. This is our power supply. No need to draw out the actual details of that. All you need to know about it is we have 120 volts AC coming in. According to the schematic, we're supposed to have 123 volts DC coming out. And at this point, it takes off and goes to the plates and other areas of the radio that require high voltage. Also from here, we have our filament dropping resistor. And then the other end of the resistor connects to our series tube filament string. Each tube, for the exception of the output tube, requires 1.5 volts DC. The output tube requires 3 volts. So when that's all added up, we come up with 7.5 volts. And each tube filament draws 0.05 amps or 50 milliamps. Now in a series circuit, everything must remain equal. Each branch must draw the same amount of current. For example, we can't have 3 tube filaments drawing 50 milliamperes and the fourth one drawing 100 milliamperes. That won't work. It'll throw the whole thing off. So essentially this filament string here draws 50 milliamperes. Now, we have 123 volts here. This filament string only wants to see 7.5 volts. So we can't apply the 123 volts directly to this filament string or we would burn the tubes out. The way we get around that is we have a big dropping resistor here to drop that excess voltage. Now the schematic says this is a 2.2 k ohm resistor, but the wattage rating of this resistor was a little smudgy. I couldn't make it out. So we used Ohm's law to figure that out. Now to calculate wattage, we multiply our current times our voltage. And to figure out how much voltage is dropped across this resistor, we simply subtract the 7.5 volts from our tube filament string from 123 volts DC right here. And that gives us 115.5 volts. That's a lot of voltage that's dropped across this resistor here. Okay, so E would be 115.5. Our current, we already know, is 0.05 amperes. So we multiply 115.5 volts times 0.05 amperes, and that gives us 5.775 watts. Now, We don't want to use a resistor that's rated right on the borderline, as in we don't want to use a 5-watt resistor here. That'd be cutting it too close, and the resistor would probably burn open prematurely. The original resistor was probably a 7-watt resistor, and those are really not that common anymore, so we'll probably end up going with a 10-watt resistor. I'll have to do some checking online and to see if any of these flex resistors are even still available, because I'd rather put one of those in there if I can. If I have to go with a standard power resistor, I'll have to get creative in the mounting of said resistor, but you know, in the case of vintage electronic repair, we do what we have to do. Okay, what I'm about to tell you now is not really going to be needed for this radio, but let's say you have one of the older 1930s radios that uses what they call a curtain burner power cord or a ballast tube, and let's say that the power cord or the ballast tube is defective. Now, in the 1930s, we didn't have the high voltage tube filaments like we had later in the 40s and up. You know, we didn't have 25, 35, and 50 volt filaments. Generally, they had 4 or 5 tubes rated at 6.3 volts wired in series. In some cases, there might be one 25 volt tube in the mix, but anyway, you still needed a resistor to drop the excess voltage so the tube filaments wouldn't burn up. Well, if you have one of these older radios and the resistance value of the line cord or ballast tube is unknown, then you need to figure out what that resistance value is, and Ohm's law to the rescue again. Resistance equals voltage divided by current. And the way we figure it out is, once again, we determine how much voltage is dropped across this resistor. And in this case, 115.5 volts. Our filament string draws 0.05 milliamperes. Now, in the case of an AC operated set from the 30s, the current draws more than likely going to be something like 150 milliamperes or maybe even 300 milliamperes. But if you don't know how much current your tube draws, you can look that information up online, or if you have a tube manual, you can look it up there as well. But anyway, we divide 115.5 volts to be dropped across this resistor by 0.05 amps, our current draw of our filament string, and that gives us 2,310 ohms. Well, there's no such thing as a 2,310 ohm resistor in the real world, so what you have to do is go with the closest thing that you can find, and in the case of this radio, they went with a 2,200 ohm resistor. That's close enough to 2310 to make it work. Okay, so hopefully you got something out of this mess. Now you know how to calculate what resistance to use when replacing one of these resistors, and you also know how to calculate the power rating of said resistor, so that should make things easier for you in the future. Well, I dug through my junk and found a couple of resistors I could parallel to give me 2.18K. That's close enough to 2.2K to use as a test until I can come up with something more proper. I have them temporarily wired in place. Let's turn it on and see what happens. Well, we have noise. Okay, that doesn't sound bad at all.
I've hated smoking all my life and never been a pain about it. Never griped about anybody else smoking until
that could be WSM.
smoke cloud if the wind's pushing.
That is, 314-282-8700.
Okay, not bad at all.
To lose, but everything to gain. 314-282.
Okay, just for the heck of it, let's remeasure our B+ voltage and see if it's within that 123 volt ballpark. Since we have a load on it now, the voltage might be lower than what it should be, indicating a weak selenium rectifier. Okay, let's see what we have here.
So that opening night, boys would like to sit on the bench and just watch those legends come out.
About 110 volts. That's about 13 volts lower than it should be, which could be a result of the selenium rectifier becoming weaker. I'll let it run a while and see if it drops down any more. Sometimes when these rectifiers heat up, the voltage output will decrease. Okay, with the 110 volts B+ voltage, let's see what our filament voltage is. 7.1. Turn that down. I don't need no copyright BS. Find a talk station, huh?
Talk 102.1 FM and 9:10 AM. WALT. Without warning, can ravage any part of the body.
Okay, filament voltage. Come on. We're getting about 6.9 volts. Well, we want to see about 7.5. And our filament voltage is a little bit critical. If it drops too low, the tubes will stop functioning. In fact, when I lower the AC input, let's see how low we can get before the radio stops playing.
Abandoned property that was just before noon. We don't know much about what they found, but the sheriff did feel the need to...
Yeah, right there. The radio stops playing. I don't really trust this meter on this power supply that much, so I'm going to measure the AC voltage and see what the actual input to the set is. But before we do that, let's see what our filament voltage is now. 6.4. So we really want to get our B+ voltage up to the 123 that it specifies. Okay, we're actually measuring. We'll round it up to 115 volts AC input. That's the threshold point for when the radio stops working. And it's just more reason for us to get our B+ up to what it should be, since the filament voltage is dependent on the B+. Because in some situations, you might not only have, but say 110 or 115 volts going to the radio, depending on where you are. And we want to have a little bit better margin of safety, so to speak, here. So we're probably going to be replacing the selenium rectifier. Okay, on the left we have the selenium rectifier that is about to be replaced by that little bitty diode on the right. A 1N4007 diode to be exact. But unfortunately it's often not quite just as simple as replacing the diode, because this diode has much less voltage drop across it than this selenium rectifier does. So if we just insert the diode in the circuit as is, our B+ voltage might be 10 to 20 volts or maybe even more higher than it should be. And in a set like this, where the filament voltage is dependent on whatever the main B+ voltage is, that could result in burning your tubes up. So we might have to add a resistor in series with this diode, but we will determine that shortly. Right now I'm just going to go ahead and install the diode as it is, bring the AC input voltage up slowly and monitor the B+, and then it'll kind of give me an idea where we need to go with this. Here's our diode temporarily tacked in. And to show you which way it goes, this is our AC input, which connects to the anode of the diode, the non-banded side. On the other end of the diode, you'll notice a little silver band that denotes the cathode. That's the DC output, and would normally connect where the plus symbol is on the old selenium rectifier. schematic-wise, our AC comes in here, and you can see the little band there on the schematic. That's our DC output. Okay, I now have the DC voltmeter connected. I have the AC power supply set to about 85 volts. And we're just going to bring it up slowly and monitor the B+ voltage, and that'll kind of give us an idea what direction we need to go in here.
This one crucial
okay, I have the AC input set.
And for that reason alone,
the filament voltage is 7.8.
If I have an X amount of dollars in my bank account,
and our B+ voltage is 120 volts.
They say, wait a minute, Mr. Hoagland,
that's within range. Okay, now let's just, for the heck of it, see how much AC voltage we're inputting to the radio.
Well, here we have for this one.
Okay, we're only inputting 111 volts AC to the radio. So if I was to crank this thing up to the standard 120 to 125 volts, it's often found today, we would have too much B+ voltage, thus too much filament voltage, which could very well lead to tube destruction. So we will need to add a resistor in series with this diode. Okay, I'm using this variable power resistor to determine what value resistor I want to use here, and I've settled on a 50 ohm resistor at 123 volts line voltage input, which is kind of on the high side. I have 8 volts filament voltage.
Here's one for you again. Look,
and 122 volts B+. That's about as far as I want to push it.
Large structures. Why in the world would you not have shown them right away to catch the attention right away of the press?
Can I jump in on that one?
Yeah, you may. Sure.
Okay. The same thing is that we discussed how to present this material, and because it's kind of a progressive process, because when you first look...
Okay.
We wanted to present it in such a way to building up to a climax to show that...
That's about the lowest AC input voltage that you can... Well, it just cut off. So let's see what our AC input voltage is now. Before it was cutting out around 115, I think. Yeah, 101 volts. So yeah, that's a nice range. So we'll say a operable range from around 105 volts up to around 123 volts. AC input, that's something I can live with. And I have my 50 ohm resistor placed between the cathode of the rectifier and this 68 ohm resistor. So probably what I'll do is just go ahead and remove this 68 ohm resistor, and I'll just replace this whole shebang with a 120 ohm resistor and be done with it. So my game plan for Monday is to go to the parts house and obtain a 2.2 k ohm 10 watt resistor for the filament. I probably won't be able to find a flex resistor anymore because those have an asbestos coating on them, and that's a major no-no now. And I'll pick up a 150 ohm, probably 5 watt resistor. Excuse me, I said 150, I meant 120 ohm, 5 watt resistor for the rectifier dropping resistor. Of course, probably what will happen, I'll go to the parts house and they probably won't have what I need, and I'll have to order the darn things. Even though this filter capacitor is still good, I'm going to need all the room I can get to add that modern ceramic power resistor. So probably what I'll have to do is just go ahead and replace this filter capacitor with modern capacitors that are much smaller, and that'll give me some more room to work as far as mounting that new resistor. Okay, that ought to about do it until Monday or Tuesday or Wednesday or whatever day I can get to the parts house. Well, I just returned from the parts house where they had a 2-pack of 2.2 k ohm 10 watt resistors. I'm very amazed, but happy at the same time that I don't have to order these. And I have our silicon diode and dropping resistor in place. I went with a 56 ohm 2 watt. I know it doesn't look like a 2 watt resistor, but resistors have gotten smaller over the years, just like capacitors have. I was originally going to replace this 68 ohm resistor with a single resistor of about 120 ohms, but had that other resistor that I just showed you, so instead of spending extra money at the parts house, yeah, I'm cheap today, I just went ahead and added the appropriate series resistor between here and here. And since there was only a few volts being dropped across this added resistor, the power dissipation didn't have to be that much, so I just went ahead with it. We have two separate resistors here, although I could have taken this 68 ohm one out and just replaced it with 120 ohm or so and been good to go. Now the fun part's going to be installing this resistor here in this area where that flex resistor formerly was located. And even though this filter can is apparently good, I think I'm going to have to replace it with smaller capacitors to give me a little more room to mount that resistor.
Well, tell us.
Okay, removing this cap is a no-go, at least for the moment. It was determined that removing this would be a major pain in the butt since it's double soldered or double-sided and soldered on both sides. I was afraid if I did too much pulling and tugging, I'd crack the circuit board, and after all this, I'd be extremely hot if I broke the chassis. So I was able to fit the resistor in there like that, and there it is, and the old capacitor stays. Now, if it ever goes bad, I'll worry about it then. And probably what I'll have to do if I'm forced to replace this is just get down in between the capacitor and the circuit board with a pair of good cutters and just cut the terminals off, and then I can remove each terminal one by one. But as it is, we're leaving it alone. Okay, I went ahead and replaced the two paper capacitors in here. One of them was a 0.05, which is no problem. Just replace that with a 0.047. This other one is a 0.33. Just simply replace that with a 0.22 in parallel with a 0.1. And before we reassemble the radio, we'll let it play a while and make sure no other problems turn up. But in the meantime, let's test the capacitors that we removed and see how they're holding up today. Here's the 0.33 microfarad capacitor. As you can tell by the flashing light, it's leaking a little bit. Since this is rated at only 100 volts, I'm not going to advance the leakage voltage test up any higher because there's no need to. And here's the 0.05. It's leaking a little bit worse than the last one. And now the 0.047 capacitor that was across the AC line. Okay, drum roll please. Let's see how bad this one's leaking. Well, I must say I'm surprised. I was expecting much more leakage. Usually those capacitors, those plastic case capacitors, don't hold up very well, especially for across the line service. But this one seems to be in, you'll see it's leaking some at 300 volts, which that capacitor is rated for 600, so yeah, it needed to go. Well, it's a good thing I didn't put it back together because I just came back down to the shop to check on it after about 45 minutes and it stopped working. We're getting noise out of the speaker, but no stations as we tune across the dial. Okay, I'm feeding the output of an RF signal generator set to 455 kilocycles into the grid of the converter tube. And as you can tell, it's passing a signal of 455 kilohertz. So that tells me that most likely the oscillator has stopped working. So we want to concentrate our efforts on that area. And also this static I'm starting to hear sounds like silver migration disease of the IF transformers. So we may now have two problems to deal with. Okay, I'm checking at the secondary winding of the first IF transformer. On the meter we have a positive 2.5 volts. That means we have a leakage inside of the IF transformer. Yeah, I can see this video is going to turn into a very, very long one. Okay, I have the offending IF transformer removed from the chassis and taken apart. What I'll need to do is somehow disable the internal mica capacitors inside of the transformer. And the way this one's made, it won't be all that easy to do, but it has to be done. And another problem is, normally whenever I do this, I can mount the capacitors, the replacement capacitors, on the underside of the chassis. Well, I probably can't do that in this case because of the way the chassis mounts in the cabinet, and with this piece that attaches to the underside of the circuit board, I really won't have any room for any components on the bottom of the board, so I'll somehow have to mount the replacement capacitors inside of the IF transformer. Also, this circuit board does have it's not cracked all the way through, but there is a crack in the board right here where the heaviest component of the whole radio is mounted, the tuning condenser. And I think that was a previously done crack. I don't think that happened since I've been working on this, so I'll have to get some epoxy and try to stabilize this circuit board and jump across any vulnerable traces with hookup wire. Yeah, this might have been a radio I should have just thrown away, but I'm into it this far, so might as well try to make it live again. A lot of guys that rebuild these IF transformers claim that 100 picofarad is the standard universal value for an AM IF transformer. Well, that's not always the case. You really need to know exactly what was used in the original transformer, and there are two ways to do that. Number one is disconnect the winding from the primary or secondary winding, and then use a digital capacitance meter such as what you see here connected across the primary or secondary side of the transformer, whichever winding you disconnected. And you can see we're reading about 35 picofarad. That's a far cry from 100. If I were to replace this with 100 picofarad, I would, best case scenario, would have to majorly realign this IF transformer. Worst case scenario, it'd be so far off that I wouldn't even be able to bring it into proper alignment. The second way to do it is disable the capacitors inside of the original IF transformer, put everything back together, and obtain a couple of small variable trimmer capacitors and solder a capacitor across the primary winding and the secondary winding, and then adjust the trimmer capacitor for best alignment, and then carefully remove each trimmer capacitor without disturbing its setting, and measure the trimmer capacitor with a digital capacitance meter, and whatever value you measure is what value of mica capacitor that you need to buy. Okay, I just got this little bag in the mail from Mauser Electronics. We have 4 36 picofarad 500 volt silver mica capacitors. The reason we have 4 is so we'll have enough to rebuild the second IF transformer if it becomes necessary. Now, what we'll need to do is disable the internal mica capacitors inside of the IF transformer. And in order to do that, we have to lift out this little brown wafer here, which looks like it's held in place by them simply seating the wafer where it needed to be, and they melted plastic over it to hold it. So we'll have to very carefully chip, cut, pry, do whatever to get that out of the way. Okay, I've got the wafer removed, and if this IF transformer ever works again, it'll be a miracle, but we're going to try. Now that we have the wafer removed, we need to bend up the little contacts that help make up the internal capacitor, and then cut off at least one of those contacts per winding for the primary and the secondary, so they won't short once we remove the mica insulator. and then we'll put it all back together and install our new mica capacitors. And here's part of the old wafer. The rest of it hit the floor, but it's a little black where it's been sparking across. It's not as bad as some I've seen, but there is evidence of SMD there. You can see that's how it looks with the wafer removed. Now we'll try to put all this back together again and resolder our one coil wire that we disconnected earlier to measure the original capacitor, and we can only hope that this will live again. If not, I've got other junk radios that might have a good IF transformer on them. Well, that IF transformer rebuild didn't go all that well, unfortunately. I ended up breaking off one of the little fine hair-like wires that I couldn't fix. So it's not a complete lost cause. We had this little GE clock radio from the mid-60s. I think we worked on this in an older video. This is the one that the tuning condenser was partially shorted in, and I never could clear the short. Well, this is the radio that provided a clock knob for our friend John in Arkansas, and it just now provided me with an IF transformer to go in this set. Now, let's just hope this IF transformer don't decide to give trouble in the near future, and it very well could, but for right now, this is all we've got. Okay, we have our IF transformer installed. No radio reception, unfortunately, but I think that's due to the dead oscillator stage, but we don't have the thunderstorm effect. Before we dive into the oscillator, let's fire up the signal generator and see if we can pass a 455 kilohertz signal through here. And we'll go ahead and peek out the IF transformers while we have the signal generator connected. Okay, with our signal generator applied to the control grid of the mixer tube, we're passing a very stout 455 kilohertz or kilocycles, whatever term you choose to use. I think I've actually used both terms during this video, but at any rate, we're passing a signal through the radio, so that just confirms that our trouble is in the front end, probably due to this crack in the circuit board, but it could be something else. Well, that was easy enough. The 1R5 converter tube went south, and this looks like a Raytheon replacement from the 70s, so enough said right there. Not surprised that it went bad. And before, I had a positive voltage on pin 4 of the converter tube.
Attached to your liberty, not so attached to your political party.
Now on pin 4, we have a negative 9.8 volts. We'll just round that up to a solid 10 volts. That's what we should have there. That indicates the oscillator is working.
Only need one. $19.99 a month.
So we'll just let this thing play a while, and if no other problems come up, then we'll see what we can do about tackling this cracked circuit board. Well, we've been on about 45 minutes and no problems, so I think now we can address this circuit board that's about to get a divorce from itself. Well, it's only been about a month since I worked on this GE radio, but I decided to patch it up this weekend and put it all back together, and it works fairly well.
38253.
Hello, this is Charles Stanley. When I think about the Christmas season and think about the fact that Jesus is what this season's all about, I think about the reasons he came. And Jesus made it very clear.
The whole of it, of the skin of it, and the seed, and it gives a bitter taste to it.
There's a 1290.
All the nutrients that's in the stem, it's in the skin.
Right. I interviewed him and I said, do you have any career goals? This is before Morgan Mindy. And
1010.
He just said, I just want to pray for the people.
I firmly, I can't predict when. I don't know when. But I'm always optimistic.
Let's see what we can get on the... Well, that may be WLW trying to, or not WLW, WWL coming in weekly. I get the two stations confused sometimes. Let's turn this light off.
And what we come to understand and
There's 670 WYLS, which is fairly hard to receive. Don't know what that is.
You know, is
910.
Got a lot of work to do.
1010. Oh, here's another weak station. I think this is a talk station out of Jackson, Mississippi, about 90 miles away. So that's not bad performance.
Now you are a whole person. What is the whole person?
That's 1290 that normally plays the R&B oldies, but they do play some religious programming and some paid programming, which apparently that's what that was. Now I see 1390 is back on the air.
ABC News on WMER.
New York City Mayor Bill de Blasio is calling for a hold on political debates and protests over police use of force until after the funerals of the two officers killed.
And there's 1450. See if we can get anything past that. There's another hard to receive station, WHOC out of Philadelphia, Mississippi.
But to really use it, certainly, and all through the town, base breaks are growing down. It's Christmas time, and Dixie 1578 wants your favorite Christmas dessert recipe. Post your recipes to the Dixie 1570 Facebook page.
Dixie 1570, I need to figure out where that station's coming from.
Go to the Dixie 1570 Facebook page, like the recipes, and try them. You might find something new for Christmas.
Yeah, I'm making a good antenna here.
At Dixie 1570,
WIZK. I think I remember receiving that station once before. Have to get on the internet and see exactly where that's coming from, but as you can hear, this radio is very sensitive to be a cheapy portable. Now, just to recap everything that was done to this radio, if I could even remember everything I've done to it myself, since it's been so long since I've worked on this. At first, the radio was totally dead due to the filament dropping resistor being opened. It originally had one of those asbestos-covered resistors. Well, obviously those haven't been made in a long time, so I had to sort of hack one of these more modern resistors in there. Then the selenium rectifier had weak output, so I replaced it with a 1N4007 silicon diode and an appropriate dropping resistor. In these portable radios, it's very important that you have the B+ output voltage within spec according to what the schematic calls for, because the filament voltage is also obtained from the B+ voltage through this resistor, and if the B+ voltage going into this resistor is too much, the output coming out of the resistor going to the filaments is going to be too much, and you don't want to overvolt these DC operated tube filaments by very much, because you will burn them out. These four tubes are wired in series, and the total filament voltage required is 7.5 volts, and we don't want to get much above that. Okay, I also replaced the old paper capacitors. I did not replace the electrolytic because it's too much of a pain in the butt to get off of this fragile double-sided printed circuit board, and it's good, so I just left it alone. Had to replace one of the IF transformers because the original one had silver mica issues. I was unsuccessful in repairing the original IF transformer, so I just installed one out of a junk chassis. Then the 1R5 converter tube went belly up right here, so I just replaced that with one out of another set. This printed circuit board is not in the best of shape. In fact, it has a nice long crack running down about in this vicinity here. Fortunately, it's not cracked all the way through and the traces are not broken. I tried to repair or should I say stabilize the board as best I could with JB Weld, but that was a little bit tricky and it didn't work too well. The only way to really repair this board is to actually break it in two, cut all the traces off, and then JB weld it back together and then run individual wires across each trace, both top and bottom of the board. And I decided that was more of a pain in the butt than it was worth. With the circuit board installed on this metal bracket and installed back into the cabinet, it's stabilized, so that's all I'm going to worry about. And I think that's all that was done to this. I thought about touching up the alignment, but as you heard earlier, it's fairly sensitive, and I really don't think there's any need to touch up the alignment. It's probably working about as well as it ever worked. Now, one other thing. Those of you who watched my video on the Aetna radio where I used a capacitor to substitute for the filament dropping resistor are probably asking yourself, why didn't you just use a capacitor in this radio? Well, simple. In the Aetna radio, the tube filaments are operated off of the AC power line. So, you know, it's okay to use a capacitor in that situation. Well, the capacitive dropper won't work in this set because we're using DC voltage to power the filaments. And a capacitor just blocks DC, so, you know, a capacitor would not work in this case. In this particular application, you have to use a resistor.
Your friends invite.
Okay, there you go. That's about all I've got for this radio. Thanks for watching, and wish all of you a Merry Christmas and Happy Holidays.
And the last way we
be safe. Don't get in any trouble.
Alexandra Levin,
and I'll be back again with something else later.
Says that in the age of tweets, text, and Facebook,
he took care of all those sick and poor people, and then started the March of God program down in Thomasville. Now, he did good at first, whether you believe it or not, he was you. And he did it. Now, you would do good work, but